Welcome back to the Math Professors. I'm Professor Van Hamlin. We're going to cover rules of logs and how to expand and condense. So please subscribe. Rule number 1 says the log base b of m plus the log base b of n is equal to log base b of n times n. So what this says is that the addition of the two logarithms becomes the single logarithm of the product of the arguments. Now similarly, for subtraction, the subtraction of the logarithms becomes the single logarithm of the division of the arguments. And really the superpower of logarithms allow us to take coefficients and to turn them into powers. It's really just repeating number 1 over and over and over again, and I'll show that to you in just a minute. So the c times the log base b of m is equal to the log base b of m to the c power. So these really are inherited from rules of exponentials, because we know that logarithm and exponentials are inverses. So what works really for these will also work for these, except in reverse, and that's because, again, they're inverses. So if we remember exponentials, if I multiply things to the same base, well, the base doesn't change. So this is condensing. So multiplying things of two base b's gives me a single base b, but the operation happens up in the exponent. That multiplication becomes addition. Very similar, if I divide things with the same base, this division becomes a single base, but the argument, but the operation happens up in the exponent, so division turns into subtraction. And then similar, b to the m raised to the c power gives you a single base b, but you're going to multiply up in the exponent. And the way I do this is I kind of look at operations that everything's built from addition. So you have addition, you have repeated addition, you have repeated addition. So addition, multiplication, and then powers. And then similarly, their equivalents in reverse, like addition and then subtraction, and then repeated subtraction, which is division. So what happens when we have things that are being multiplied? Well, for exponentials, if you're multiplying things to the same base, the base never changes. The operation turns into plus. So multiplication gets turned into the addition of the powers. Similarly, if you're dividing things with the same base, that the operation is going to happen in the exponent, that the base is going to stay the same, but you're going to subtract the exponents. And similar, when you're raising powers to powers, the base isn't going to change. So raising powers to powers, you're going to multiply the exponents. So you can see that with exponentials, your operation is always going to be one strength less, and that operation is going to happen in the exponent. Now, similar for condensing logarithms, I'm going from multiple logarithms to a single logarithm, just like how from multiple exponentials to a single exponential. This is now going to go in reverse. That addition of the two logarithms is going to condense to a single logarithm, so the logarithm won't change. It'll condense to a single thing, just like this condensed to a single base. But the operation is going to happen, in the argument of the logarithm. So the argument of the exponential is the exponent. The argument of the logarithm is the inside piece. So addition is going to turn into multiplication. Again, the log base won't change. We're just going in reverse. Now, similarly, subtraction is going to turn into division. And lastly, multiplication is going to turn into powers. So let's use these things to expand and condense. So I want to write the logarithmic expression as a single logarithm. So really what I'm asking to do is condense the logarithms. So what I have here is the natural log of x plus the natural log of a and y. Remember, the natural log is nothing more than the log base e of x plus the log base e of y. So natural logarithm is just log base e. Now I don't need to write that. I know that's what this is. So what we know is that addition becomes, so let's do our little trick over here. So if I'm adding things, I know I'm going to multiply inside the argument, so the logarithm is not going to change. This is going to become a single logarithm of just the multiplication of its arguments. Now similarly, I wanted to show you that where powers actually come from and why this works. So what we know we can do is that this is the addition of three logarithms. So very similar, that addition is going to turn into multiplication. So this is going to be the log base 2 of, x, because it's this one, times x, which is this one, times x, which is this one. So really this gives us the log base 2 of x squared. So this is the log base 2 of x, cubed. Now remember, also, this thing right here is the something plus something plus something, which really represents 3 times those things. So up top, this also represents 3 log base 2 of x. So 3 log base 2 of x is the same thing as the log base 2 of x cubed. So that's really what we just verified there, just really using this rule right here. Now if I want to use this rule, multiplication turns into power. So if I have 3 log base 2 of x, I can just put that power on top. All right, so let's condense this. Well, what we have to do is we have to handle the exponents first. So for me to actually combine these logarithms, they're going to have coefficients of 1. So the first thing we're going to do is take care of step 3 first. So coefficients become powers. So this is going to be the log base 2 of x cubed minus the log base 2. 1/2 is the same thing as square root, so I'm going to write the square root of y plus 2 minus the log base 2 of z to the 4th. Now we're going to handle 2 at a time. So let's do this piece first. So what I know is that subtraction is going to turn into the division of the argument. So these 2 logarithms are going to condense to a single log base 2 of the division of their arguments. Now we still have the log base 2 of z to the 4th. Now again, I got 2 logarithms and subtraction turns into division, so this is going to be the single logarithm of, this argument divided by this argument. We'll show it the long way first. Now this complex fraction can be simplified, that really this is, z to the 4th over 1, so I can multiply by the reciprocal, which is going to allow that z to the 4th to go at the bottom. So finally this is going to be the log base of 2 of x cubed all over, I'm going to write the z to the 4th first, and then the square root second. Now you'll get really, really good at this. Looking at these very long logarithms and then write it as a single logarithm. So what we can see is that these 3 logarithms, or no matter any chain of addition and subtraction, is going to turn into a single logarithm where the coefficients are going to become the powers. So, if it's positive, this is a positive 3, notice that I have that x cubed up in the top. This is a negative half, so I'm going to have a 1/2 power on the bottom, so this is going to be to the 1/2 power on the bottom, and this was also a subtraction, so I was going to have a z to the 4th on the bottom as well. So let's do one more and then see if we can't do it quick. Okay, so this is our last example, and you notice I didn't put any bases on here. The reason I didn't put bases is because when the base is omitted, really this thing represents base 10 things. So this is actually the log base 10 of x plus 4 times the log base 10 of y minus 3 times the log base 10 of w plus 5 times the log base 10 of z. So if you see ln, it's log base e. If you just see log, that is log base 10. So you don't have to write the 10s back in there, and I will leave those off in a second here. So my goal really is to kind of quickly write this as a single logarithm and see if we can get this idea quickly adapted. So what I know is that this is a chain of addition and subtraction. So what I'm going to get is a single logarithm. And since I have both pluses and minus, I know some things are going to be on top, some things are going to go on the bottom. Now this is a negative, so this is going to be on the bottom. And remember, this coefficient is going to become a power, but negative means division. So I'm actually going to have an x squared on the bottom. Similarly, this is a positive, so this will be a y to the 4th on the top. This is a negative, so it's going to be on the bottom, so it'll be a w cubed on the bottom. And then finally, this is a plus, so this is going to be a z to the 5th on the top. Now we could do this, 2 at a time. So let's take care of the powers. This is log base minus the log base. Minus the log base of x squared. Or you can say x to the minus 2 if you want to. You can see that's going to be an x squared on the bottom regardless. So plus 4 times the, I want the powers up top, log of y to the 4th minus the log of w cubed plus the log of z to the 5th. Now I guess I can leave this as a negative here. We know that's going to be division. It doesn't matter. Either way, you're going to get an x squared on the bottom. So 2 at a time. So I actually have subtraction here. This is this minus this, so this is going to be the log of this y to the 4th is going to go up top, and this x squared is going to go on the bottom, and then I still have minus the log of w cubed plus the log of z to the 5th. Now handle these two. Subtraction means division, so I'm going to get that w cubed on the bottom. So this is going to be the single logarithm of this argument with a w cubed on the bottom, plus the log base of z to the fifth. And finally, addition becomes multiplication, which really is just going to stick a z to the fifth up top. That's how we get this. Let's go backwards. The logarithms. Well, this is just going in reverse. That the logarithm of the product is going to be the addition of the two logarithms. So this multiplication is going to turn this into two logarithms. So this is going to be the log base 3 of the first plus the log base 3 of the second factor in this argument. Now similarly, this is division, so division is going to turn into subtraction. So this is the log base 8 of the numerator minus the log base 8 of the denominator. Let's write this as a z plus 1 to the 1/3 power, because that's what cube root means. Now the last step I can do is if they have powers, you can turn them as a coefficient. So this is 2 log base 8 of x minus 1/3 times the log base 8 of z plus 1. And then our last example for this is going to be C. What about the log base 4 of So what about the log base 4 of x to the fifth square root of y all over w squared and also a z down there. So let's start out with how we handle this first. We have to take care of the biggest operation inside of here first, so that's going to become subtraction. So this is going to be the log base 4 of the numerator minus the log base 4 of the denominator. Now I can handle each one of these pieces separately, so this multiplication is going to turn into addition. So this is the log base 4 of the first factor plus the log base 4 of the second factor. Let's write this as a y to the 1/2. Now remember, I have minus this, so I'm going to put this in parentheses. Because even though this turns into a product, this is going to be the opposite of whatever I get here. So this is going to be the log base 4 of w squared plus the log base 4 of z. Now, since this is subtracting both of these things, if I drop these parentheses, this negative will extend to that last term. And then the last step is just to put the coefficients in front. So 5 log base 4 of x plus 1/2 log base 4 of y minus 2 log base 4 of w, and then finally minus the log base 4 of z. All right, one last example. I want to use exponential rules and logarithm rules to really show that these things really are kind of equivalent to each other. So given the log base 2 of a is 5, the log base 2 of b is equal to 7, the log base 2 of c is equal to -3, I want to evaluate these things using expansion. So right now I don't have this as the log base 2 of b or c. I have the log base 2 of this full argument b cubed times c. So what I know is that multiplication is going to turn into addition. So this is going to be the log base 2 of b cubed plus the log base 2 of c. Now, that's good because I know the log base 2 of c. So this piece right here is -3, but this is still not done. I need the log base 2 of b to be isolated, so we can go ahead and pull out that 3. So now what we have here is I know that the log base b of 2 is 7. And then similarly, I know that the log base b of 2 of c, log base 2 of c is equal to -3. So I can make direct substitutions here that this is going to be equal to 3 times, well, the log base 2 of b is going to be equal to that 7, plus the log base 2 of b is going to be equal to this -3. So what we're going to have is this is going to be equal to 21 minus 3, which is going to be equal to 18. Now similarly, we can do this as well. So this is going to be equal to, got to handle the biggest operation here, so the division first. So log base 2 of the numerator minus the log base 2 of the denominator. We'll handle the powers last. So now this is still a complicated argument, but a multiplication turns into addition. So this is going to be the log base 2 of a squared plus the log base 2 of b minus the log base 2 of c cubed. And last, we can take care of their powers. So 2 log base 2 of a plus the log base 2 of b minus 3 times the log base 2 of c. And again, I know some of these values. I know the log base 2 of 3. I also know the log base 2 of b. And I also know the log base 2 of a is equal to this. So this is going to be equal to 2 times whatever that is, plus whatever the blue thing is, minus 3 times whatever the pink thing is. So log base 2 of a is 5. The log base 2 of b is equal to 7. And then the log base 2 of c is equal to negative 3. So what we're going to get here is 10 plus 7 plus 9. So this is going to be equal to 25. 26. Try that again. There we go. All right. I wanted to show you this using, we'll do the complicated one, but I wanted to show you using exponential rules and then the inverse property of logarithms to prove this to you. So what I want to do is I'm going to simplify this argument in terms of base 2. So using the first one, I know that this can be written as an exponential, that a is equal to 2 to the 5th power. Now for this one, I know that b is equal to 2 to the 7th. The way you get rid of this log base 2 is I'm going to exponentiate both sides by 2, right? That'll cancel the logarithm, so I'm just going to get a back. Similar here, I'm rewriting this as an exponential. 2 to the 7th is equal to b. And then last, rewriting this as an exponential. 2 to the negative 3 is equal to c. So when I have this log base 2 of our a squared times b times c cubed, this is going to be the log base 2 of, well, a is 2 to the 5th, that thing's being squared, times b, which is 2 to the 7th, all over c cubed, well, this is going to be 2 to the minus 3. Now, instead of using the rules of logarithms, we're going to use the rules of exponentials, knowing that they're equivalent. So we'll get the same answer. So let's handle this first. We have to do these powers to powers first. So this is going to be 2 to the 10th times 2 to the 7th, all over 2 to the minus 9. Now let's do the multiplication first, and then we'll do the division last. So 2 to the 10th times 2 to the 7th is going to be 2 to the 17th. 2 to the 17th. So this is the log base 2 of 2 to the 17th, all over 2 to the minus 9. Now when you divide, you're going to have to subtract the power. So this is going to be log base 2 of 2 to the 17th minus a minus 9, which is the same thing as adding 9. And we know that 17 plus 9 is 26. So this is going to be equal to the log base 2 of 2 to the 26th. Now we know that log base 2 and exponential base 2 are inverses, so these will annihilate to give us just that power of 26. Again, if you like the videos, subscribe.